pump. So if you remember, in case of a pump, diffuser pump, you remember a diffuser pump, or that was also called turbine pump. That time I told you that why it is called turbine pump, because of its similarity with that of turbine. So you see here, this reaction turbine here, especially the Francis turbine, its working is very much similar with that of a pump, but in opposite direction, in reverse direction. Clear? Because if you remember, in case of pump, the water enters at the center, it flows over the veins, moving veins, then the guide veins, which we call as diffuser. Clear? And then the water was discharged, clear, through a discharge pipe. But now in this case, everything is reverse. So what happened is that, if you see here, the water it enters, this is the spiral casing. So as the water enters, you can see here that there is a decreasing flow cross section. As the water flows, there is a decreasing flow cross section. So it means that the kinetic energy is converted into this pressure, that is converted into kinetic energy, because when flow area is decreasing, the velocity is increasing. Clear? So the pressure energy that is partly converted here into kinetic energy. Then this water, we have the guide veins. I show you the picture before. These guide veins, these are stationary veins. You see here, these are guide veins. These are stationary veins. They just guide the water so that the water enters into the moving veins at required angles. And the purpose is to reduce the shock loss that we studied in pumps also. So it guides the water so that the water can enter into this rotating element here. This is the impeller in case of pump, but in case of turbine, this rotating element, it is known as a runner. So the water enters into this runner, and as the water flows over the veins, this runner is rotated, and you see at the center, then this runner is rigidly connected with the shaft, and the shaft rotates. So this is how the hydraulic energy that is then converted into mechanical energy in the form of rotating shaft. So these veins here, which you can see, these veins, these are the runner blades, runner veins or runner blades. Clear? So this is how the working of reaction turbine takes place. This is Francis turbine, because you see the water moves along the radial flow. Clear? You see everywhere the movement of water is along the radius. So that's why we say it is radial flow, inward radial flow. Similarly, the flow can be axial, as in case of Kaplan turbine, and the flow can be mixed flow, partly radial flow. Clear? So this is a typical example of Francis turbine, and it is named after James B. Francis. So I already explained the working. Energy of the fluid partly transferred to kinetic energy before it enters the runner. So as you can see, the flow cross section is decreasing. So the energy, pressure energy, that is partly transferred to kinetic energy before it enters the runner. Now it enters the runner with excess pressure. Clear? The flow that is striking the veins, that is under pressure. Clear? Because in case of impulse turbine, no pressure, atmospheric pressure, the jet of water. So that is the kinetic energy that is acting on the buckets of impulse turbine. But in this case, because the wheels run full, the wheel runs full of water. So that's why the water enters the runner with the pressure. This pressure energy that is converted into kinetic energy as the water passes through the runner. The difference in the pressure between the inlet and outlet of runner, that is reaction pressure, is responsible for motion of runner. So this is how the reaction turbine in general it works. The examples can be Francis turbine and can be Kaplan turbine. Now this is the Francis turbine scroll case. So the water will enter here from the penstock and it will move all around here. It will move all around. You see the decreasing flow area. And then the water will enter here. You see the water will enter and then the water will flow over the veins. The water will flow over the veins, and as a result, this runner, it will be rotating, and this runner will be connected to the shaft. It will be connected to the shaft of generator. And as a result, the shaft will be rotating. The shaft. So this is how the hydraulic energy will be converted into mechanical energy in the form of rotating shaft. So this is the scroll case for Francis turbine. This is the guide vane assembly showing wicket gates and control mechanism. You can see here that the water will enter through these gates. These are guide vanes. Clear? The water will enter through these guide vanes. So this is for the case of Francis turbine. This is the runner, as I showed you before, the runner of the Francis turbine. So the water will enter at the center. They will rotate these vanes. These are the vanes or blades. They will rotate. And then because of rotation of the vanes, the shaft of the generator will be rotating. And this is how the hydraulic energy that is converted into mechanical energy. So this is the runner of Francis turbine. You can see in this diagram the size. And this is the reaction turbine, but the type is propeller type. The type is propeller type, Kaplan turbine. In this case, you can see the water will enter through these gates or vanes, stationary vanes. The water will enter from both sides here. And then the water will flow here along the axis of, parallel to the axis of rotation. So that's why you can see here that this is a propeller type of turbine. The direction of movement of flow is parallel to the axis of rotation. So as a result of which this will rotate. This will rotate. And then the water will join the tail race. So when this will rotate, it will rotate this shaft. You can see here, this is the shaft, it will rotate. And then this will be connected to the generator. This is what we have in the powerhouse. So this is connected with the generator. And generator converts this mechanical energy into electrical energy. So you can see the flow through the propeller turbines, or we can have a mixed flow where the flow is partly radial, partly axial. So the conditions are rather complex. That's why the analysis of these turbines, these are not given in our textbook. You can find the analysis in more specialized book, but these are not explained in detail in our textbook. Clear? So only we have the radial flow, Francis turbines, these are explained in detail, and the Pelton wheel. This is the difference between the impulse turbine and the reaction turbine. I already explained the working of the two types of hydraulic turbines. So you can study by yourself. For example, you can see if we consider this number 1, all the available energy of the fluid is converted into kinetic energy by a nozzle that forms a free jet. So that's why the nozzle, that is integral part of the impulse turbine. But there are no nozzle in reaction turbine. See, in the reaction turbine, you did not see any nozzle. So only a portion of the fluid energy is transformed into kinetic energy before the fluid enters the turbine runner. Because of the scroll casing, the flow area is reducing. So only a part of that pressure energy that is converted into kinetic energy. But as the fluid flows over the blades of the turbine runner, then the transfer of energy takes place. This is the case in reaction turbine. So you can study all the remaining by yourself. I already explained the working of the two types of turbines. This is now the figure which is given in our textbook, that is called the tube turbine. So you can see here that from the headwater, the water is supplied through these penstocks here, tubes, tunnels, penstock, and you can see that it will rotate. This is a propeller type. You see the flow is parallel to the axis of rotation, and then the water will join the tail race. So as these turbine it rotates, it will rotate the shaft of this generator, and hydraulic energy is converted into rotating shaft mechanical energy by the turbine, and then generator it will convert this mechanical energy into electrical energy. Now, as I said before about governing of turbines, so you see that if the load on the turbine drops, we need to reduce the speed, control the speed, because normally for best efficiency, the pumps and the turbines, they should operate at a constant speed. So because if the load on the turbine drops, we need to reduce the flow of water so as to control the speed. Because this amount of water is driving this turbine, so for that purpose these gates are provided for reaction turbines. So the flow of water that is controlled by operation of these gates. Clear? So now we study in detail about the reaction turbine. We studied the head acting on impulse turbine. Now we study the effective head that is acting on reaction turbines. So now this is the reaction turbine. The wheel run full. That's why you see the turbine is shown here. The wheel is rotating in a horizontal plane. Clear? So the wheel of the Pelton wheel, it was like this, and this is how the jet is acting, and this is how the wheel rotates. We have the different vanes or blades here. This is how it rotates. In case of the reaction turbine, this will appear as horizontal. You look from here. So this appear as horizontal unit. And this is how it will rotate in a horizontal plane, and it will then rotate the shaft, which will be connected here. So it will rotate the shaft. So the water will come here, can be from both sides, and it will rotate in a horizontal plane, and then the water will join the tail race. So this is how it appears. Reaction turbine. Now, how to calculate the head which is acting on reaction turbine? Again, we see that we have this head, this A point here, and we have this C point in the tail race. So the head that we consider, that is the difference between these two. The head that is the difference between these two, that is the gross head that is available to the turbine. This is the gross head that is available to the turbine. Now out of this gross head, because we have submerged discharge, so the water is in motion here, because in case of impulse turbine, the water just falls down here after striking and it joins the tail race. But in case here, you see that the tail race, the water is moving. So at a velocity, at point C, the velocity is not zero, very, very small, but not zero. So that's why the net head that we want to calculate, that will be minus this Vc square by 2g. You see, it is above this tail water by this head. This is this here. So this is the net head, and this net head, it will be equal to what? It will be this gross head minus this Vc square by 2g minus these head losses, which are head losses in the penstock. This is the pipe which supply the water to the turbine. So head loss will occur in this pipe. So the net head, it is just from here to here. From here to here. It is less than the gross head. How much? By this HL and by this small velocity Vc square by 2g. It is very small, but still this is considered as a loss. Clear? So this is the net head. Now this net head which is available acting on this turbine here, this will include at point B is here just upstream of this turbine. We have this PB by gamma plus VB square by 2G, the velocity head which is here. The velocity head which you can see there, the velocity head. So this net head, it is PB by gamma plus VB square by 2G. So this is the net head. If you remember, the net head was up to here in case of impulse turbine. But in case of reaction turbine, this ZB, this is also acting on the turbine. Why it is acting on the turbine? This is due to this draft tube. Draft tube is nothing but it is a increasing area pipe which is provided, which connects the turbine with the tailwater. So because of this draft tube, this Z which was lost in case of impulse turbine is not lost in case of reaction turbine. You understand? This head, because of the draft tube, this head is not lost. It is acting on the turbine. This head was lost in case of impulse turbine, but in case of reaction turbine, because of the draft tube, if you do not have the draft tube, it will be lost. So because of the draft tube, this head is not lost. That's why draft tube is considered integral part of reaction turbine. Because it increases the net head on the turbine, the power generation, the power available can be more. So that's why this draft tube, which is nothing but a pipe, increasing cross-section pipe, which connects the turbine with the tail race. So this is the draft tube. So what are the purposes of draft tube? Now two primary purposes of the draft tube. What are the two primary purposes of the draft tube? Number one, it increases the net head on the turbine. So the head which was lost in impulse turbine, it is not lost in case of reaction turbine. So this is the first purpose of this draft tube, that it increases the net head on the turbine. And the second purpose is because you see here the draft tube which connects this turbine and the tail race, you see the turbine will run full. So in this case, the turbine is here or it is here. It doesn't matter because the wheel runs full. So because of the draft tube, we can set the reaction turbine above the tail race without losing the head. And why we need to place the turbine above the tail race? Because we need it for inspection purposes. Even if this wheel is submerged in this water here, still no problem, still the turbine will work because it is already submerged in water. But we want to place it above the tailwater for inspection purposes so that we can easily inspect the turbine. Clear? As you can see here, in this case, the turbine, for inspection purposes, we can easily inspect the working or any problem. So that's why this draft tube, it helps without losing the effective head, the turbine to be placed above the tail race. So these are the primary purposes of the draft tube. That's why draft tube is considered integral part of the reaction turbine. So how to calculate the net head now? For a reaction turbine, the net head H is the difference between the energy level just upstream of the turbine and that of the tail race, as we discussed. So the head that is available to the reaction turbine, it is PB by gamma plus VB square by 2G plus ZB. You see here ZB is not lost. This is due to the draft tube. That's why draft tube is integral part of reaction turbine. and because this is considered a loss, so minus Vc square by 2g. But it is written in our textbook. Normally, usually this is very small, it can be neglected. So this is the head that is available to the reaction turbine. Now that this is the head that is available to the reaction turbine, we say that in most cases this Vc square by 2g, that is very small and may be neglected. So this is very small and it can be neglected in most cases. Now this is the head that is available to the turbine. If we compare this with the head available with the impulse turbine, so for the case of impulse turbine, what was the head available? The head available was Pb by gamma plus Vb square by 2g. If you compare the two, it means that the head that is available to the reaction turbine is more than the impulse turbine. That's why, thus for the same setting, the net head on reaction turbine will be greater than that on Pelton wheel. So it means that for the same setting, the power generation by reaction turbine will be more than the power generated by the impulse turbine. That's why nowadays we prefer the reaction turbines. You go to Turbela Dam, you go to Varsak Dam, you go to Ghazi Barota hydropower project. Most of the cases we are utilizing reaction turbines. Clear? Because these impulse turbines, they are suitable for high heads. When very high heads are available, then we can use this Pelton wheel. So you can see that for the same setting, the net head on reaction turbine will be greater than that on the Pelton wheel. Now, as I said, the draft tube that is considered as integral part of reaction turbine, thus the effective head H dash, this is now H dash, see H dash that is available to act on the runner of reaction turbine is this. This is H dash that is available to the acting on the runner of the reaction turbine. So it is this H which is coming from here minus these losses. So what are these losses? This is the loss, friction head loss due to friction in the draft tube. Because the draft tube is considered integral part of the reaction turbine, so as the water flows in the draft tube, there will be friction. So that is coming here. And this is the loss at submerged discharge. We already studied about this minor losses in our chapter 8 pipe flow. So this is the submerged discharge loss. When these two are subtracted, this is H dash that is available to act on the runner of the reaction turbine. The head H double dash which you saw for impulse turbine, the head H double dash that is actually extracted from the water by the runner is smaller than H dash by an amount equal to the shock loss at entry to the runner. What is the shock loss? This is when the water enters into the blades, there is a mismatch. So the water does not enter smoothly. The vanes or blades of the turbine, that we call it as shock loss. So that is considered as a loss. And the hydraulic friction losses in the scroll case, guide vanes and the runner. So out of this H dash that is available to the runner and the head that is actually extracted by the runner, that will be H double dash. So now this H double dash is similar to H double dash in case of impulse turbine. When we come here, we discuss here H and then we shift it to H double dash. So this I told you where is H dash. So this is now same as for the reaction turbine. So that's why we say H double dash. So this H dash is here. So now H double dash, that is consistent with the impulse turbine H double dash. So this is the power that is actually extracted, gamma Q into H double dash. That is actually extracted from water by the runner. Clear? So now that we have these losses, so we can define efficiency of turbines. So the overall efficiency, as I said, we have hydraulic efficiency. We can define hydraulic efficiency. We can define the volumetric efficiency. We can define the mechanical efficiency. But these are no longer explained in our 10th edition of the textbook, and then the overall efficiency will be the product of these, the total final output divided by initial input. So now in the 10th edition they no longer explain these. Maybe in the 8th edition you can find detail about these. So the overall efficiency of the turbines is the final output, that is the shaft power, the brake power, divided by the initial input. So that is the overall efficiency for the turbines. So the overall efficiency is the final output. This is the final output, rotating shaft, and this is the head available, the initial input. Of course we have the losses. That's why we have hydraulic efficiency, then mechanical losses, mechanical efficiency, and if there are leakages, the whole water is not utilized, so we define the volumetric efficiency and so on. So this is the overall efficiency, the final output divided by the initial input. Clear? What is available and what is the final output, that defines the overall efficiency of the turbines. These are the different terms. Gamma is specific weight, flow rate. T is the torque delivered to the shaft by the turbine, and omega is rotative speed in radians per second. So whenever we write down omega, that is in radians per second. Sometimes the speed can be given in revolutions per minute, RPM. So if it is given in RPM, you can convert this into radians per second using this relationship. So this is how we can calculate the efficiency for turbines. You see, for pumps, what was the efficiency? Opposite of this. For pumps, what was the efficiency? The efficiency was, the output was gamma QH. Clear? The efficient output was gamma QH, and the input was the shaft power, T omega. But for the pumps, it is T omega divided by gamma QH. That's why pumps and shaft, they are the opposite machines. Next, we discuss about the specific speed of the turbines. We already discussed about the specific speed of turbines for pumps. The same concept applies here. So specific speed of turbine, that is expressed by this equation, NS, specific speed, and NE is the rotative speed, that is corresponding to the maximum efficiency. BHP is the shaft power, brake horsepower, the shaft power that we defined here, T omega. This is BHP. And H is the head acting on the turbine. So these are the values for NE, the BHP, shaft or brake horsepower, and the net head in feet, that are corresponding to the maximum efficiency. Clear? So this specific speed, this is more related to the geometry. It says that two turbines of identical geometric shape but of different size will have the same specific speed. Clear? They are identical. Now this is the graph which is available in our textbook. So we see for a single nozzle impulse turbine, this is the specific speed. Remember, this is in the British gravitational system. H is in feet, shaft power is in horsepower, and NE is in RPM. So in the British gravitational system, they defined. Now in our textbook, the graph for SI system is not available. For SI system is not available. So you can find other fluid mechanics books. They also give the graph that is develop our range of values for specific speed, that is in SI units. But in the book, in our textbook, it is written that because of difficulty of carrying everything in different units, so they only give the equation that is related to this graph, and this is only for the British gravitational system, not for SI system. You can refer to other books if you are interested to find the graph that is developed for SI system of units or ranges. They give ranges and tables for SI system of units for these different types of turbines. So this graph is only applicable for this equation for these units. So you can see that the specific speed, it defines the type of the turbine. Whether we have a single nozzle impulse turbine, whether we have a Francis turbine, this is the curve, Francis turbine. Or we have a propeller turbine, the specific speed is more. This is the curve for the propeller turbines, clear? And also we have this peripheral velocity factor that we defined and studied in pumps. The same concept apply here. So you can see here, this is the phi E curve for the specific speed, and this is the phi E for the Francis turbines, and this is the phi E for the propeller turbines. And we studied that phi E is used to estimate the diameter of rotor. In case of pump, it is impeller, and in case of turbine, it is runner. So this is very useful concept in the preliminary design and selection of pumps and turbines. That's why we study about the specific speed. So now in this case, the specific speed, that is also known as type characteristic, because it indicates the type of turbine. Now specific speed can also be selected on the basis of available head of water. This is not given in our textbook, but I mention here from another book that turbines can also be selected on the basis of available head of water at the site. This is just a guideline. So we say that if the head is 0 to 25 meter, you can select Kaplan or Francis, preferably Kaplan. 25 to 50 meter, Kaplan or Francis, preferably Francis. 50 to 150, this is the suitable turbine is Francis. And as the head increases, then you can see that Francis or Pelton, preferably Francis. 250 to 300, Francis or Pelton, preferably Pelton. And above 300 meter, the suitable turbine is Pelton wheel. So this is just a guideline. Remember, this is just a guideline. This is taken from another book. This is a guideline that on the basis of available head, we can also select a suitable turbine for that site. Clear? And also the peripheral velocity factor that is linked with this specific speed here, you see from these graphs here, for the different types of turbine. So you can see that for different types of turbines, these phi E, the peripheral velocity factor, that vary approximately as for impulse wheels, this is 0.43 to 0.48, for Francis turbines 0.7 to 0.8, and for propeller turbine 1.4 to 2. So what is the significance of this peripheral velocity factor? We already studied for the pumps. The same concept applies here. Peripheral velocity factor. So it is the ratio of the peripheral velocity to under root 2 GH. This is known as the peripheral velocity factor, denoted by phi. For the turbines, phi is U1 divided by under root 2 GH. You remember for pumps it was U2. For turbines it is now U1. You remember this was U2 for pumps. For turbine it is U1. Why? Because you see, let's say this is the blade of a pump. So the water enters at the center. This is the center. Clear? This is, let's say, the center point. The water enters at the center, then it flows over the vane. So this is U1. This is now the inlet. This is U1. The speed of this blade, this is at U1. And here it is U2. And this is the water exits. Clear? So for pump, we consider U2. This is for the case of pump. U2 here. But in case this is the center and this is the blade of the turbine, then the water enters here. This is the inlet. This is U1 in case of turbine. and this will be U2. So this is for the turbine. So that's why when it rotates for a pump, we consider U2 in here, and for a turbine, we consider U1 here for this peripheral velocity factor. So U1 is the tangential velocity of a point on the periphery of the rotating element. As with pumps, as we already studied for pumps, for any given turbine, phi will vary over a range. But we are interested in phi that is corresponding to maximum efficiency. Let phi E be that is corresponding to the maximum efficiency. So then we can use this expression from here. D is equal to this expression, where D is the diameter of the wheel or runner of the turbine. In the British gravitational systems, then this is the equation. Same equations that we developed for pump. But the difference is there was U2, and now for turbine it is U1. So this equation can be used to estimate the diameter of the runner for Francis and propeller turbines, but not impulse turbine. So this equation we can use to calculate, estimate the diameter. You see, these concepts are used in the preliminary design. We can estimate the diameter, and what diameter? The pitch diameter. You already now know the runners for the Francis turbine and the propeller turbines, clear? But not the impulse turbine. So in impulse turbine, we cannot use this equation to calculate that pitch diameter that we discuss. The pitch diameter that we discuss in case of impulse turbine, you cannot calculate using this equation, clear? This equation we can use to estimate the diameter of the Francis and propeller turbines, because see the conditions that we apply. This condition does not apply to the impulse turbines. Now we solve a few problems to apply the concepts that we just learned. So this is chapter 16 of the textbook. So it's problem 16.3. Now consider an impulse turbine with a pitch diameter. Now you know what is the pitch diameter, and the bucket angle beta 2 is given 168 degree. If the jet velocity is 55 meter per second, the jet diameter 100 millimeter, and the rotative speed 300 rpm. Find the force on the buckets. Part B is the torque on the runner and the horsepower that is transferred to the runner. And we assume the exit relative velocity to be 0.85 times the inlet relative velocity. So now that we have to calculate the force on the buckets, so that's why we need to draw the inlet and outlet velocity diagrams for the impulse turbine. We need to draw the inlet and outlet velocity diagrams for the impulse turbine. Then we can estimate the force, because we have to calculate the change of velocity. So that's why this is the inlet velocity diagram for Pelton wheel, impulse turbine, inlet velocity diagram. So you see all the three velocity vectors, they are parallel to each other, indicating that alpha 1 is 0. Alpha 1 is the angle which V1 makes with U, so 0. And beta 1 is 0. Beta 1 is the angle which relative velocity makes with U, 0. And we draw the exit velocity diagram or outlet velocity diagram. So the jet is deflected by 168 degree. This is our beta 2. Relative velocity makes with U, so beta 2. And this is alpha 1. We can calculate if required, alpha 2. This is alpha 2. If required, we can calculate. So now we know the inlet outlet velocity diagrams, so we can calculate the force. We have to first estimate the change of velocity. So we need to calculate the velocities at inlet and exit. Now u is equal to r omega. This is the relationship between the angular speed and the linear speed. As you studied in physics, maybe in the school colleges, linear velocity and angular velocity, v is equal to r omega. So here u is equal to r omega. So omega is given, that is in rpm. So that will be 2 pi n by 60. 2 pi n by 60, this is omega. And this is your n, small n. This is given in rpm. So multiply by the pitch diameter. The pitch diameter is 2.6. So that's why radius will be half of that. So this is u. Now we calculated u. V1 is given 55 meter per second. We can calculate small v1, the relative velocity at inlet. So v1 is given, u we calculated. Now we can calculate this small v1, the relative velocity at inlet. So v1 is 13.4 meter per second. Now that v1 is known, the small v1, we can calculate the small v2, because it is given that the relative velocity at the exit, at the outlet, that is equal to 0.85 times small v1, the relative velocity at the inlet. So that we can easily calculate 0.85 times small v1. Now v2, small v2 x is equal to v2 cos of this. So it is minus 11.15. Now we have this small v1 and we have the small v2. We can calculate the change of velocity. So the change of velocity is minus 24.55 meter per second. Similarly, you can calculate v2, that is here v2, its component in the u direction. In the u direction, its component in the x direction. So the absolute velocity, that is equal to this absolute velocity of the vane or blade into this relative velocity component. And if you remember, whatever is the shape of this triangle, we have this relationship. We proved this for the 3 cases, that whatever is the shape of triangle, this will be the relationship between the 3 velocities in the u direction when we studied momentum and forces in fluid flow. So this is how this equation is used. So we calculate v2x as this much, v1 is 55. So we can calculate delta v, which is minus 24.5. So you see, the change of relative velocity is the same as the change of absolute velocity. That's why in the u direction, you calculate the force. Considering absolute velocity or relative velocity, you will get the same answer. So we consider f is equal to change of relative velocity or change of absolute velocity, you will get the same result. Q can be calculated from this equation, and you plug in the values, rho q delta v, this is the force. Now we get negative answer here. Where this negative answer goes? Because we say that this is the bucket. This is the bucket, ellipsoidal bucket with a splitter in the middle. So this is the force. This is the force of bucket on water. So this is in opposite direction, this is negative. So this negative makes the negative sign here as positive. So we get plus sign. Clear? And then this is the correct direction. So what will be the force of water on the buckets? It will be equal and opposite. This is what the concept we use in momentum and forces in fluid flow, chapter 6 of the textbook. So this is the force that we calculate here. Force of water on buckets in this direction, equal and opposite to this. Now the torque will be F into R or D by 2. F into R or D by 2. So this is the torque that you can calculate, and the power transferred, the horsepower transferred to the runner, P is equal to F into U, or you can also use tau omega, you will get the same result. So this is how we calculate the power that is transferred to the runner. Next we have this another question problem 16.14 from the textbook. We have a 36-inch pipeline. F is given, friction factor here for this pipeline here. It is long, connecting a reservoir whose surface elevation is 1800 feet. So this Z1 here, this is 1800 feet. And the nozzle at an elevation of 1000 feet here. So the nozzle here, this line here, the datum, that is 1000 feet. Is used to drive the impulse wheel. If head loss through the nozzle is given by this expression, now this is the head loss given in the nozzle, we already discussed. Determine the horsepower that will be developed by the jets having diameters of 8-inch, 10-inch and 12-inch. And part B of the question is on the basis of answers to part A, approximately what would be the horsepower and diameter of the jet that gives the maximum horsepower. So now you apply energy equation here, you consider this point here and another point here. You apply the energy equation. And also we have the continuity equation. So what is the continuity equation? This is here d square into v is equal to dj square into vj square for the jet of water and for the pipe, the continuity equation. And then you combine the two, because in this equation v is unknown and the diameter of the jet is unknown. That we consider because it is given. So later on we will put the value. So when you combine these two, the energy equation, this is the friction loss, Darcy-Weisbach formula, clear? And the continuity equation, when you combine the two, we get this equation. Now in this equation, we have velocity of jet and we have the diameter of jet. So now this equation, we can put 8-inch diameter of jet, 10-inch of diameter of jet and 12-inch diameter of jet, and we can calculate the horsepower. So what we do for the given values of dj here, 8-inch, 10-inch, 12-inch, we can find vj from here, this equation. Once you calculate vj, then we can calculate the discharge, and once we know the discharge, we can calculate the power. So this will be gamma q into vj square by 2g divided by 550. This will be in horsepower, because it is given in horsepower how much is the power. So now we take first 8-inch. For 8-inch, then this is the diameter in feet, this is the velocity from the previous equation, area of jet we can calculate, discharge from here we can calculate. You can calculate the velocity head for the jet of water, and using this equation we can calculate the power. Similarly, we go for 10-inch. For 10-inch, this is the power, and then for 12-inch, this is the power. So now the part B of the question is on the basis of answers to part A, what would be the horsepower and diameter of jet that gives the maximum horsepower? So this gives the maximum horsepower. It does not mean that you just keep on increasing the diameter of jet, the power will be increased. No. You can see here for a diameter of 10-inch, the power is maximum. So you have to provide this for maximum power. So the maximum jet power of 6510 horsepower, that is for the jet diameter of 10 inches. Next is problem 16.31. So now in this case, find the specific speed of a turbine that runs at a maximum efficiency of 90% at 300 revolutions per minute under a net head of 81 feet with a flow rate of 50 CFS. Now we have to estimate the runner diameter. So now the overall efficiency is given. We can estimate the brake horsepower, because we already know that efficiency is equal to In case of pump, efficiency is equal to BHP, that is the T omega, the output, divided by the input, which is gamma QH. Clear? So efficiency multiplied by gamma QH divided by 550 is the brake power, brake horsepower, shaft power. So now BHP is this much. Then the specific speed equation is given for the turbines. We know all the values, just plug in the values. So we calculate the specific speed as 25.1. Now we can determine what type of turbine is this. So you will use figure 16.4 in our textbook with specific speed of 25.1. What type of turbine is this? 25. This is 30. Let's say in the middle, this is 30. 25 will be here. So for 25, what type of turbine is this? Francis turbine. And that is the corresponding efficiency. So now we need to calculate the runner diameter, estimate. This is the phi value that you will take. This is the phi value. So this is around how much? This will be around 0.7 from the figure. If you accurately draw, this will be around 0.7 from this figure. So now from this figure, this phi E is around 0.7, and we just discussed this equation to estimate the diameter of the runner for the reaction turbines. You plug in the values. So the diameter of the estimated diameter of the runner, that is 3.2 feet or 39 inch, multiplied by 12, 39 inch. So this is the estimated diameter of the reaction turbine.